Good morning, Dr. Seyfried. It's a true pleasure to have you on the podcast today. Obviously, we'll be discussing all things cancer in short order, but before we get into it, would you mind introducing yourself to the audience for those who aren't familiar with you and your body of work?
Yeah, well, thank you, Rob. It's nice to be here. I'm a professor of biology at Boston College. I have been here since 1985, 40 years now. And before that, I was at Yale University in New Haven, Connecticut. Here at Boston College, I've taught a broad range of classes over the years: neurobiology, neurochemistry, neurogenetics. Now I teach general biology to the non-majors, as well as an advanced class in cancer metabolism. Cancer is a metabolic disease. So our background for biochemistry was lipid biochemistry. I did a lot of work on lipid biochemistry, and as far as diseases are concerned, lipid storage diseases, as well as genetic diseases, epilepsy in particular. And now our main focus over the last quarter of a century has been predominantly cancer, but we are moving into also other chronic diseases as well. So I have a kind of a broad based experience. I have a degree in genetics and biochemistry, a master's degree in genetics. Those are the background the background educational experience that I've had.
That's incredible, and a resume I suppose I could only dream of. I think one of the big issues in the health podcast space is creating content that is sort of based on actual science, and to have someone with your background and credibility, I feel at least hopefully sort of highlight that we're not here just to obviously discuss pseudoscience today, that this is all sort of based in empirical data. Dr. Seyfried, and I know we're here to really talk about the metabolic theory of cancer, but I think it would be prudent to maybe start off with having a quick conversation about what cancer actually is. And I know it's likely a dull question, but I do feel it's that very few people actually know what the disease is. It's just something that they aim to just not get. I've got a few questions there, but yeah, maybe we could just start off with that, a cancer biology 101, as it were, if you would just mind running through what cancer is.
Well, it's actually it's a complicated problem, but it's a very simple definition of what cancer is. It's cell division out of control, dysregulated cell growth. So people say, well, what's cancer? It's just a bunch of cells that are no longer regulated in their growth. Of course, the origin of that phenomenon is broad, but what is it that makes a population of cells in a particular organ of someone's body to start growing in a dysregulated way, as opposed to normal cell division, which is regulated? In parts of our body, there's wear and tear. Cells naturally die and are replaced, but the replacement of dead cells is a very organized process. They grow, they divide, and they, however many divisions is necessary to replace those that are missing, is a well-regulated process. And we know now that's all controlled by the mitochondria. But an example of cell division under control, is in the gut. You have the crypt cells that seem to always replace other cells in a very regulated way. And in the liver, you have liver regeneration. Liver is an interesting organ because if you remove a lobe of the liver will regenerate the missing part of the lobe, and the speed of liver regenerating cells is just as fast as that of the fastest cancer. The only difference is that the liver replacement liver regeneration is regulated growth, whereas a hepatoma of the liver, which is liver cancer, is dysregulated growth. And the biochemistry of those two populations is strikingly different. So when you ask what is cancer, it's dysregulated growth in a population of cells in someone's organ, which differs from regulated growth of cells in that organ.
So sort of out of control mitosis, you might say, in a nutshell.
Yeah, and the question that has perplexed the field for decades is what is responsible for regulated growth in the first place? Why would one cell know when to stop growing and another cell not know when to stop growing? And that all comes back to the role of the mitochondrion in the cytoplasm. The mitochondrion controls calcium signaling within the cell. Nobel Prizes have been awarded for people to learn the cyclins and going through the cell cycle. And that cell cycle is all controlled by calcium signaling from the mitochondria. So when mitochondria of the cell become dysfunctional in the sense of producing energy and that calcium gradients, they fall back on a fermentation metabolism, which is an ancient form of energy without oxygen. And the mitochondrion loses control of the differentiated state.
That being anaerobic respiration.
Yeah, anaerobic. You can grow cancer cells in the absence of oxygen or in the presence of cyanide, and they survive. So which would normally kill normal cells, and that's because their energy metabolism is of an ancient type. It's the type of energy that existed on the planet before oxygen came into the atmosphere 2.5 billion years ago. It was a fermentation metabolism, generating energy without oxygen. And the default state of cells is proliferation. The default energy state of cells is fermentation. So what cancer cells are doing is they're simply falling back on their default proliferative state and their default energy state, behaving much as they were of all cells that existed before oxygen, which was unbridled proliferation. And they would die as soon as the fuels that drove the fermentation metabolism would dissipate in the microenvironment, and the cells would die. So it was purely an energy-driven process without regulation. During the origin of life on the planet, archaeobacteria fused with other cells to develop the mitochondrion. And it was the mitochondrion that allowed the division of energetic labor in the cells, allowing metazoans to form and the most complex multicellular organisms that we have today, all due to the energy capacity of the mitochondria. And the nucleus, which everybody seems to have focused on, is because you could see it, sometimes even with the naked eye, whereas the mitochondria for centuries could not be seen clearly until you had the electron microscope and more sophisticated ways of looking at this organelle. But in a nutshell, it's the mitochondrion that controls the regulation of genes in the nucleus. So all this epigenetic stuff you hear about is mostly mitochondria controlled. So the nucleus is kind of an obedient slave of whatever the mitochondria does, because if that organelle becomes corrupted, the cell falls back as in one of these dysregulated growths. So everything comes back to the origin of cancer as a corruption of mitochondrial function, only in cells that can switch to the ancient fermentation pathways, which can explain why certain cells in our body never become tumor. Red blood cells can't become a tumor because they have no mitochondria or nucleus in the first place. Neurons of our brain cannot sustain fermentation. So you rarely, if ever, get cancers from neurons. They get from glial cells.
What about cardiac tissue?
Cardiac tissue rarely, if ever, gets cancer because they cannot replace oxidative phosphorylation with substrate-level phosphorylation. So you rarely, if ever, get cancer of muscle, striate, or cardiac tissue because they die. And you can't get a cancer cell from a dead cell. So we're able to go through the body and look at the kinds of tissues that form cancer because they have the capacity to transition from oxidative phosphorylation to substrate level phosphorylation which is a protracted event. It doesn't happen overnight. You really have to abuse the hell out of your mitochondria in a chronic way to get cancer. Cancer is very hard to get. I know it's exploding as an epidemic, but we abuse the crap out of our bodies, and that's why we're getting so much cancer. But it's really hard to get cancer. So when you say, well, how come so many people? Because their bodies have been chronically abused by a variety of insults, many of which they're not even aware of. But that's how you get cancer. It's a chronic disruption of oxidative phosphorylation coupled to a compensatory substrate level phosphorylation. And Warburg knew this a long time ago from the 1920s, but he only knew that it was a glucose-driven transition. But we now discovered and have, I had the concept, but not the evidence, but now we published a big paper recently that the cancer cell can ferment an amino acid called glutamine. So you get sugar and amino acid fermentation are driving the dysregulated growth of the tumor cell. And the field all thought it was glutamine respiration, oxidative, but it's not. It's glutamine fermentation within the mitochondria itself. So the very organelle that's supposed to get energy through oxidative phosphorylation is also producing energy through substrate level phosphorylation, which is a fermentation mechanism. This is what's blowing the doors off the field. They never realized that the very organelle could also ferment. And that goes back to its origin as a bacteria itself. So, once you understand evolutionary biology, all the pieces of cancer fall into place quite reasonably.
No, it really does. And I just love the fact you brought up the mitochondria as being more than just this sort of this energy factory of the body. It's just involved in so many epigenetic processes beyond just helping to create ATP. And yeah, thanks for that. It really does sort of provide some context to what is going for the rest of the conversation. I reckon the natural follow-up there, and again, this is quite a loose question, I suppose, is I suppose, and you've already answered this to a degree, but at sort of and beyond the sort of the metabolic side of it, I'd love to sort of get your thoughts on the different theories that are sort of driving cancer. Obviously, it's a complex. There's complex etiology there, and it shouldn't be viewed from this sort of reductionist viewpoint that there is just one mechanism that causes cancer. I know in my brief experience in academia that people studying these conditions can often get wrapped up in their own mechanisms and occasionally be blinded by research. Obviously, you have a fairly well-rounded view. So would you mind talking us through the various sort of, and I hope I sort of phrase this correctly, proposed triggers maybe or underlying mechanisms that sort of lead to the development of this condition, sort of the genetic causes, the environmental risk factors, the immunological side of things. I don't know if I phrased that correctly or if that makes sense.
Yeah, well, it does. I mean, when you look at the history of the disorder that has intrigued scientists, for centuries, we knew about cancer a long time ago. Virchow, in the 1800s, people were studying these things. And how does it start? You have the emergence of different ideas, concepts of what cancer, what cancer is. The current view, taken by all major research centers and academic centers, is that it's a genetic disease. I know the UK thinks that. The United States government, National Cancer Institute, believe that. I think most of the cancer institutes around the world, the French, the Germans, the English, all Western major, and even in China and Japan and Korea, South America, they're all of the view that cancer is a genetic. It seems to be some sort of a paralytic mindset throughout the world. It's an indoctrination, a brainwashing, if you will, of what this disease is supposed to be. But it wasn't always that way. There was the viral cancer was a virus caused by viruses. And cancer was a metabolic disease. Cancer is a genetic disease. So you have to put all the views over time into what it is. And Warburg started the idea that it was a mitochondrial metabolic disease. but he couldn't explain certain things which we now can explain. He didn't know about the glutamine issue, nor did he realize that a lot of the oxygen that cancer cells consume is not used for ATP, but produces reactive oxygen species, ROS,
Yeah.
which are radicals, and they cause, in large part, the mutations in the nucleus. So, certain viruses. Okay, well, we knew certain like papillomaviruses and hepatitis viruses and the Rouse sarcoma virus. Peyton Rouse was a Nobel Prize receiver for his virus particle. We now put all that together. We know all these viruses damage oxidative phosphorylation chronically, causing this transition to substrate level phosphorylation. But it was the Watson and Crick DNA structural analysis that kind of sent the whole field off into the abyss, chasing stuff that we are still chasing, because it became exciting to bring a very complicated mishy-marshy disease back into a molecular configuration. And I think that was, I call it physics envy. Biology had always been a poor stepchild to the pure rational thought of the human mind, which was physics. When the DNA structure was defined and you could explain the arrangement of amino acids and RNAs all linked back to the structure of the DNA, biology was brought from a observational kind of a disorder or a field into a more quantitative way. Yeah. And then, of course, as soon as you started looking at cancer cells, you start to see chromosomal abnormalities. That goes back to Theodore Boveri, who knew nothing about cancer. And he said, I think cancer might be something to do with chromosomes. Purely speculative. He even said, I'm probably wrong about everything, and he was. But the field grabbed a hold of him as the father of the genetic theory of cancer. And then, of course, you started to see gene mutations associated with certain cancers. And then we spent billions of dollars on the cancer genome projects, looking at every kind of a mutation. And then therapies, precision and medicine and all this developed around the genomic view of cancer, where we're going to have precision medicines, targeted therapies, and all this kind of stuff, which is where we are today. And all the governments and academic institutions are giving away millions of dollars in grants to people trying to hunt down genes that could be responsible for the dysregulated cell growth. So it comes back. What we know, cancer is a dysregulated cell growth. What's causing that?
Yeah.
Well, according to the Somatic Mutation Theory, which is the dominant theory today, it's mutations that are causing that. But I've clearly shown that those mutations are largely irrelevant. With our research, that's ahead. They can't attack it because the evidence is too strong. So when you have evidence that's overwhelmingly strong and it's not consistent with your general theory, then you ignore it. But you're only going to ignore it for so long. So when you develop a theory, theories are supported by a massive amounts of evidence. The Somatic Mutation Theory was very, very strong because you found almost all cancers with somatic mutations. And these somatic mutations, some of them were linked to the cell cycle, which you could then link a mutation in the genome to something that would lead to dysregulation or dysfunction of the cell cycle. And that made a lot of sense. So people grabbed onto that, and because it was so molecular and so quantitative and approachable by really sophisticated technologies which have developed around cancer, like all these sequencing, unbelievable AI now, artificial intelligence helping analysis of sequencing, and all of the different kinds and types of mutations that were found in cancer cells. I mean, it was an explosion of molecular biology associated with cancer. So that was very attractive to a lot of people. But then, having done work in my lab and seeing research that was far more consistent with what Otto Warburg said than with the Somatic Mutation Theory, I began to look at this. But getting back to theories, I like to compare what's happening today with the mitochondrial metabolic theory replacing the somatic mutation theory, because it really takes a lot of evidence to replace a theory.
Yeah.
Einstein's theory of relativity could still be replaced, but it has not yet been. And there are physicists that are constantly trying to show where Einstein was wrong, and they believe they might, but they haven't. Darwin's theory of evolution has been challenged many times, but it has not been overthrown because the data that support it are stronger than the data that don't support it. And then you have the geocentric, heliocentric theory of the solar system, where for 1,800 years people thought that the Earth was the center of the solar system.
Yeah.
And we developed equants, deferents, and epicycles to try to predict the positions of the planets. And Copernicus just replaced the Earth with the sun. And all of a sudden, a lot of stuff was far less complicated and more understandable. So the heliocentric theory replaced the geocentric theory, opened up a scientific revolution during the Middle Ages, the Renaissance period. What we're having today is that mitochondrial metabolic theory is overturning the somatic mutation theory, and the consequences are going to be every bit as phenomenal as what happened during the Copernican revolution. So we look at evidence to support a theory. If cancer is a disease of somatic mutations, which is the current dogma, irrefutable truth, the silent assumption, cancer is a genetic disease. Well, now with deep sequencing and deeper analysis, we find some cancer cells that don't have any mutations, yet they're growing out of control. So when I looked at those, there's not many papers, but there are some very clear findings. And then when I say, what do the investigators who believe that cancer is a genetic disease say about cancer cells that don't have mutations or they can't find any mutations? And they don't say anything. So when I went back and looked at their explanation, they ignored it. They didn't even talk about the cancer cells that had no mutations. They just seemed to focus on all the cancer cells that had mutations. And I said, you got a glaring inconsistency in your theory staring you in the face, and you did not address it. What the hell's going on with that? Then, of course, they realized that there's so many hundreds of thousands of mutations in some of these tumor cells. They all can't be drivers of dysregulated cell growth. So then the field decided to reclassify some of the mutations as passenger genes and driver genes. So we then moved into the driver gene mentality, which lasted several decades, where only some of these many mutations are truly responsible for dysregulated cell growth, and we redefined them as called drivers.
Yeah.
And that generated a lot of excitement since the early 1980s, I guess, mid 80s, driver genes, the driver genes. So now with deep sequencing and more sophisticated technologies, we're finding all kinds of mutations in driver genes in our normal tissues, like you and me. I mean, we got all kinds of mutations in P53 and MYC and RAS and all these kinds of genes that are in our normal tissues and are not dysregulated in growth. How you explain that? That's inconsistent with your somatic mutation theory.
Yeah. Are there any real sort of polygenic risk scores maybe that have been identified in respect to this?
The nuclear mitochondrial transfer experiments that's the real nail in the coffin for the whole thing. Because what was done on a variety of different types of cancers is that the nucleus of the tumor cell is now placed in the cytoplasm of a non-neoplastic cell. And invariably, you get regulated growth, despite the continued presence of whatever kind of genetic abnormality might have been in that nucleus, whether it was polygenic, whether it was chromosomal, whether it was point mutations, frame shift mutation. Didn't make any difference. When that cancer nucleus was placed into the cytoplasm of a non-cancerous cell, that new cell no longer had dysregulated cell growth. That's quite interesting. And that's been done repeatedly, and in vivo and in vitro. So in all kinds of experimental systems, meaning that normal cytoplasm suppresses neoplastic growth. On the other hand, if the nucleus of a normal cell is now placed in the cytoplasm of a tumor cell, you got dysregulated growth, which is completely the opposite of what you would have expected on the somatic mutation theory. So when you have the opportunity to sit down and carefully evaluate all of the evidence from the nuclear mitochondrial transfer experiments, also, if you have a raging tumor cell and you replace the mitochondria with normal mitochondria, just put normal mitochondria, you get complete downregulation of this dysregulated growth. You can convert a raging tumor cell into an indolent tumor cell by putting normal mitochondria back in the cytoplasm, mitochondrial medicine type.
I was about to say, I'm getting ahead of my curve and I'm going to shoot myself in the foot by asking this question now. But just with regards to that, then, is there any a thought to the idea that mitochondrial transplants could be a potential therapy in that regard?
Absolutely. But but that's the future. It's not here yet, because we have to make sure that the mitochondria that are transplanted are normal in number, structure, and function. And during the very process of manipulating these mitochondria, you can also damage them, and you have to know how to do that. So mitochondrial medicine is going to be the future, but where the technology to do that is not here yet. So our approach to managing cancer is killing the tumor cells while not harming the rest of the body, and then allowing people to live far longer with a higher quality of life, while mitochondrial medicine is under development. that's the thing. You know, it's very interesting because when you have dysregulated cell growth in cancer, they're fermenting like crazy, and the oncogenes, which have generated tremendous interest, we have shown, and others, HIF1 alpha, MYC, and these things, they are there. And they are facilitators of opening the floodgates for fermentation fuels to get into the cell. And when you put new mitochondria into the cell, the oncogenes turn off. You don't need them anymore. Why are you going to ferment when I can respire? So the oncogenes are no longer needed, and normal mitochondrial respiration turn off oncogene expression. So you shut down the glycolysis and the glutaminolysis pathways because you don't need glucose and glutamine. You can respire. Everything is makes perfect sense, and the data show that. So where did all the mutations come from? They came from the biology of inefficient oxidative phosphorylation, throwing out reactive oxygen species, which is the superoxide and the anion, the OH radical, which are carcinogenic and mutagenic. And they come out of the dysfunctional mitochondria, creating an escalating situation of biological chaos. So what we're seeing, or what the field is mostly focusing on, is downstream epiphenomena of the damage to mitochondria and all the sequelae that follow that. You know, it's really amazing to me. I just can't figure out how the field doesn't understand this. I don't know, maybe I have to write it in crayon. Maybe you know, sometimes you just have to do that. You have to take the back of a neck and smash the guy's face into the evidence to let him see it. But the interesting thing is that you see all these clear evidence that you can manage this disease quite effectively by just depriving the cell of the two fermentable fuels that it needs, and then transitioning the whole body over to fuels that the tumor cells can't use. So intrinsically, people say, oh, cancer cells are so tough and hardy, and they're so versatile. That's total crap. How do you explain a cell with a nucleus blown to hell with all these mutations, and you're going to have that cell behave more transitional and more flexible than the cells in our body that evolved over millions of years to adjust their metabolism to the situation? And the cancer cell can do this with a nucleus that's blown to hell? Makes no sense in evolutionary biology. People don't understand evolutionary biology. The way you understand cancer and many other diseases, you must understand evolutionary biology. And if you don't do that, you're going to be in the dark. You're going to be in the dark. And that's what explains a lot of the stuff that we have in medicine today, because if people don't understand evolutionary biology, they remain in the dark. And as long as you remain in the dark, you ain't moving forward. So, here's what they say. Oh, cancer cells are tough to kill because we're throwing everything at radiation and chemo and immunotherapies. And those damn cancer cells can survive. Or they're protecting themselves with the waste products of fermentation metabolism. They say, everybody knows, they say, oh, the cancer environment is so acidified, it protects them from the therapies that we have. Where does the acidification come from? The waste products of glucose and glutamine fermentation. If you take away glucose and glutamine, you remove the acidification of the microenvironment, making the tumor cells extremely vulnerable to small doses of radiation, chemo, and these other procedures. How is that not understood by guys that are supposed to be smart? Don't you understand why the damn tumor cells are not dying from what you're throwing at them? Because they're fermenting. If they ferment, you take away the fermentable fuels. Oh, that can't be right. It's too simple. Yeah, and it works, and it is right. Get over it. You want to live longer, you take away the fermentable fuels, and then you give them fatty acids and ketones, and you say, and the cancer cell can't, because you need a good mitochondria. You need fatty acids and ketone bodies cannot be used as a fuel by cancer cells because the mitochondria are inefficient. Fatty acids and ketone bodies can be used by most of our normal cells because we have good mitochondria, healthy mitochondria. So we lower the blood sugar, elevate the ketones, and then come in and target the glutamine pathways strategically in an approach that we developed, the press pulse therapeutic strategy. Glucose is a non-essential metabolite. Glucose is a non-essential metabolite. We can live with very, very minimal levels of glucose just to keep our erythrocytes moving oxygen and CO2 through the body. It takes tiny amounts of glucose. But the majority of muscles and brain can all transition over to ketone bodies. Tumor cells cannot. We tested them. We interrogated these cells. And tumor cells collect huge droplets of fatty acids in the cytoplasm because they cannot use the fatty acids. If you force the tumor cell to use the fatty acids, it develops reactive oxygen species and explodes and dies. So that's why they store the fatty acids in the cytoplasm, because if they try to use them, they're going to kill them. So this is simply a protective mechanism. I can't tell you how many people are writing papers saying tumor cells love fatty acids because they store them in the cytoplasm because they need them for fuel. Yeah, we'll try to goose the cell to use the fatty acids, and all of a sudden the cell dies. Try to grow your cells, your cancer cells, in the absence of glucose and glutamine, in the presence of fatty acids and ketone bodies. With no glucose, no fermentable fuels, they die. So it becomes very clear how to manage cancer. So we're aware of this. Unfortunately, the field still has to come to grips with this, and I think they slowly are, but it takes time, unfortunately.
Yeah, no, I think we could probably stop the podcast there. That was incredible. Thank you. I'm definitely going to have to re-listen to a bunch of that.
Well, not only re-listen to it, read the damn papers that we published. I go into great biochemical details. I have the evidence put out in those papers that we publish, and they're open access. So everybody can read them. Anybody with a few functional brain cells can sit down and read these papers and make their own decision as to what they think in light of I do a compare and contrast the theories. I do the evidence supporting the different theories, and you tell me what you think is happening. And I learned there's very few people that actually understand, or not understand, who actually read the literature. They all wait, and they only do what other people are doing, and they ask other people what they think. And if the person says, "Oh no, it can't be," okay, then I believe it can't be. Why don't you use your own brain cells and analyze the data for yourself? That's one of the great things about humans is we have a rational mind. That's what we were gifted with. But I'll tell you, dogmatic views, political, religion, all that takes away from rational thinking. And when you lose your ability to sit and rationalize, then you lose a part of your humanity. And what we're seeing here, the reason why there's a delay in the movement from the Somatic Mutation Theory to the Mitochondrial Metabolic Theory, which will prevent and manage diseases dramatically. We're going to drop cancer death rates like there's no tomorrow. We're going to keep people alive because we understand the science supporting what we're saying. And then once people start looking at it and seeing that we are essentially correct, not on all the minutia, we can always work out minutia later on. But the bottom line is, how long can I keep somebody with a stage 4 tumor alive? Oh, he's got 3 months to live. Are you kidding me? We've got people that we're giving those they're still alive 5 and 6 years later because they've transitioned their body over to nutritional ketosis and came in with certain low dose medications to kill off the tumor cells. So I know it's going to work because I've seen enough preclinical studies and human studies, small trials, to know this will work and keeps people alive. Unfortunately, you go to the top hospitals and they tell you, oh, no, you got to have this. Did you ever hear that cancer is a metabolic? No, I never heard of it. Eat sugar. Eat all the high carbohydrate diets. Why? Oh, because you're losing weight. Why am I losing weight? Well, you have cancer and we just try to poison you. Anybody who's poisoned loses weight. So you get nausea and vomiting, diarrhea, fatigue. Why are you doing that? Well, we used the toxic poison on you. Why are you doing that? Well, we're trying to kill your tumor cells. I went bald. Why? Why you go bald? I lost all my hair. Did you have tumor cells growing in your hair follicles? No, they just happened to die. Why? You're trying to kill tumor cells, not kill your hair or blow out your gut. And that tells you those are the procedures of people who lack knowledge. What we're seeing is the result of massive lack of knowledge on the biochemistry and biology of the very disease that people are working with. And we're using medieval therapies that are torturing people. I think people during the Spanish Inquisition would be very impressed with how we're torturing cancer patients in these hospitals. They could say, well, we could learn something from you guys. Where do I get red devil, doxorubicin? We could give that to a heretic. It's terrible for me to say stuff like this. But, when you see 1,700 people a day in the United States dying from cancer, 70 people an hour, and you see cancer getting worse and worse around the world, I mean, grab somebody by the throat and say, what the hell are we doing? Why are we allowing this to happen? Because of a failed theory. That's what it is. A theory that's no longer supported by the evidence. And you guys keep treating people based on an incorrect theory, and the outcome is abysmal.
Yeah. What did Einstein say? Insanity is doing the same thing over and over and again and expecting a different result, something to that extent.
Yes.
I believe. Yeah.
Well, why are they doing? Don't they know what Einstein said? Did they not hear what Einstein said?
Yeah.
And there's another issue of morality, which is even a worse issue. And you don't like to be referred to as an immoral person. But when you're taking drugs that are not based on the correct theory and treating people with them and knowing that they won't work, and that's immoral. And the other part of this is that many of those drugs are very, very expensive.
Yeah.
And what happens, they not only cause physical toxicity, they cause financial toxicity. Many people, their marriages dissolve, they commit suicide. The cost is passed on to the surviving relatives. And for folks that are not well off, a $20,000 bill, even though they covered 80% of the 100,000, 20,000 can cripple a family with limited means. This is immoral. The whole cancer industry is an immoral industry. They're allowing people to suffer and die based on an incorrect theory, and they're allowing physical and financial toxicity. These are immoral acts, and we have a strategy that can absolutely reduce the deaths of cancer, keep people alive with a higher quality of life, and it's not being done anywhere on the planet. Now, you tell me what's wrong with that.
Yeah, I'm not even going to try and sort of answer that question just at this point. Dr. Seyfried, again, that was an amazing answer. Thank you. I'd just like to take a step back quickly and have a quick discussion about your thoughts on testing. Now, the way I see testing is it's generally done quite acutely when somebody presents with a disease. In this case, you'll obviously get a physical exam done, some sort of imaging, probably some sort of biopsy as well, some blood tests looking at various biomarkers, etc. But in no way is this sort of testing preventative. It generally is only treated and dealt with when the issues arise. Now, obviously, there are various technologies that are starting to sort of come up, things like liquid biopsies. Maybe you could elucidate on that slightly. And these full body MRIs, which are obviously somewhat controversial in the sense that they may or may not pick up incidentalomas. The idea of finding an issue that may not be an issue that then requires further investigation that then may or may not actually turn into an issue. What's your stance on early detection as a whole? Do you think it's something we should be exploring more beyond just the basic get your colonoscopy done when you hit 40 plus? Or does the whole thing again about incidentalomas and treating cancer from that perspective, not treating and scanning for cancer from that perspective generally make it a bit of a moot point?
Yeah, well, you have a couple of things here to break down. The diagnostics, I'm in favor of non-invasive diagnostic approaches. If we have a liquid biopsy that's 95% accurate in determining whether or not you have a neoplastic growth somewhere in your body, I'm all for that. And then, non-invasive imaging, whether it's a PET scan, MRI, CAT scan, or one of these kinds of things. I'm not in favor of biopsy because I have seen so many papers published in the scientific literature showing that when you stab a cancer, you run the risk of causing metastasis, metastasis, where the spread of the tumor, the cells can spread around your body, making what was formerly a localized problem a systemic problem. So I'm in favor of for diagnostics, colonoscopies and breast things and stuff like this. Those are, I don't know what to say about that. I know there's a lot of controversy about that. Most people who develop cancer have certain physical signs that in their body that something is wrong. Like you said, a lump, a wound that doesn't heal, blood that continues to come from some location. Those can be then liquid biopsy to see if there's a real linkage to some neoplasia, a scanning of the body or something along these lines. And then once you would make a diagnosis without a biopsy, you see a lump. Okay, let's launch into metabolic therapy and see if we can shrink the lump naturally with diet drug combinations, non-toxic drugs and diets that we've developed here at BC. And if you shrink the lump and it goes away, well then, and the imaging analysis and the liquid biopsy data, what happened? Where did it go? I don't see any of the markers that were there previously. That's great. And if it doesn't go away completely, you might have shrunken it down and make it much smaller, in which case a surgical procedure or a dose of radiation at a very defined spot could be potentially curative. So there's a lot of ways to diagnose and treat cancer in early stages, different than what we're doing today. We're too radical on this whole thing. You see a lump and rip the person's breast off or something like this. I don't know what to say about colonoscopies or breast exams. Breast cancer rises every year in females in this country. Colorectal cancer is on the rise, so I don't know what's going on. All the major cancers seem to be, many of the major cancers seem to be on the rise and happening in younger and younger people.
Yeah, if you were to speculate, do you think that is an environmental issue, just sort of maybe excess sort of xenoestrogens in the environment that are particularly, just from a breast cancer perspective, maybe triggering these issues, or is that a bit reductionist again?
I think most of it is environmental. There are some people who have genetic predispositions to insults from the environment. You have to realize that cancer is a disease. In fact, not only cancer, most of the chronic diseases that we are dealing with, which is dementia, type 2 diabetes, obesity, hypertension, high blood pressure, so a lot of neuropsychiatric problems, are all the result of mitochondrial dysfunction in one way or another, caused by the diet and lifestyle that we're all under. And we know this pretty much because Paleolithic man would not have had any of these kinds of conditions. They died predominantly from infections and injuries. They did not have orthopedic surgeons to repair a broken knee from some guy, gored by a buffalo. Um, and how do we know that? Because people say, well, you weren't there during Paleolithic period 500,000 years ago, but we have people on the planet who still live according to traditional ways, and these folks also didn't have cancer or a lot of the chronic diseases that we have today. How do we know that? Because Albert Schweitzer and a number of other physicians and humanitarians were investigating these primitive tribes, and they said, wow, they're remarkably different from those that live in the United States and England. So they were not obese. They didn't have any chronic diseases. They had bacterial infections, parasites, and things like this. So what's the difference between the Western diet and lifestyle and the Paleolithic diet and lifestyle? And predominantly, it's the availability of highly processed carbohydrates in our diets. Paleolithic man never had highly processed carbohydrates in his diet. We did not evolve to evolve in an environment with highly processed carbs.
By highly processed carbohydrates, are you talking, obviously, and my evolution biology is definitely not my strong point, but I assume you mean sort of very high GI carbohydrates, things like your processed sugars, honeys, etc., opposed to things like root vegetables, things that are potentially lower on the glycemic scale that maybe
Yes.
wouldn't, yeah.
Yes, predominantly things that can live in remain edible in a package. Like I have a Twinkie here. This Twinkie is 10 years old, and it looks edible. And it's 10 years old, and a mouse ate it, broke in and ate one of these 2 years ago, and he didn't complain. And there are people that are hungry that would eat one 10-year-old Twinkie. This is a synthetic thing made from all chemicals and sugars. This kind of stuff will kill you. Yet we eat large amounts of it. Not only that, we deep fry it and put powdered sugar and chocolate syrup on the damn thing.
You should go to Scotland. That sounds like breakfast.
Yeah, right.
Yeah.
So then we wonder why we got cancer and high blood pressure and hypertension, and neuropsychiatric problems. And the lack of exercise is unbelievable. Paleo, you know how hard it is to track down and kill a big animal? It's not easy. You have to have runners. You have to have strong guys to track down and kill these buffalo, and you have to kill a mammoth, a woolly mammoth, and these kinds of big animals that lived in Paleolithic times. And that was a lot of energy to kill, not only to kill the big thing, but to chop it up and eat it. They'd go for the bone marrow as a fuel source that was very rich in nutrients. We're sitting in traffic today. We're sitting in front of computers. We don't nearly have the amount of energy that was expended during Paleolithic times. We're eating highly processed carbs, bad food. We have bad sleep. We have emotional stress. We have all of these things that impact negatively on the number, structure, and function of mitochondria in our cells. It is not surprising that we have all of the chronic diseases and cancer that we are currently suffering with in modern Western societies. It's absolutely understandable in terms of our evolutionary biology. We are still Paleolithic man biologically, but living in a modern industrialized society where all of the desires that we would have had in Paleolithic time are now at our fingertips in any supermarket. We don't have to go out and hunt down animals. Everything is prepared, packaged, and ready for us to eat right away. We don't have to expend a lot of energy to cook it up, kill it, and cook it every night. It's preserved, well preserved, so we can store it for a long period of time and eat it. And eventually, it beats the hell out of your mitochondria in your body. And some people, you get obesity, type 2 diabetes, hypertension, high blood pressure, macular degeneration, dementia, cancer. Every one of those diseases disorders is the result of mitochondrial dysfunction in one way or another. Some cells up and die, become dysfunctional, not becoming cancer. Some cells that have the capacity to switch from oxphos to substrate level phosphorylation become cancerous. So we can link all of the major chronic diseases, including cancer, back to mitochondrial dysfunction, which then begs the question: well, how do you prevent cancer? And you keep your mitochondria healthy. It's extremely difficult to get cancer if your mitochondria are healthy. Well, how do I keep my mitochondria healthy? Do a lot of exercise, stress management, avoid highly processed carbohydrate foods, try to get good sleep, do all the things that keep mitochondria healthy, and you don't get dementia, you don't get cardiovascular disease, you don't become obese, you don't get cancer. You significantly reduce the risk for cancer and all these chronic diseases by keeping your mitochondria healthy. You know, it's very interesting. In the United States, the NCI National Cancer Institute says we reduced cancer by 33% over the last several decades, mainly because we had the anti-smoking campaign of the 1990s. And if we all continue to smoke like crazy, like we were in the 1990s, we would have 33% more dead cancer patients today than we actually have. So clearly, the major drop in cancer deaths came from the elimination of a provocative behavioral situation, which was smoking. So why? Because our mitochondria are healthier when you don't smoke. And everything comes back to the health and vitality of the mitochondria. Do we want to go back and become, again, living in a cave like Paleolithic man? No.
No, but finding that happy middle ground.
Yes, but now we have an awareness. And not only that, we developed the glucose ketone index calculator.
My next question was going to be exactly that.
Which is now going to be the tool to allow every person that has can measure their blood glucose and ketones with a meter, either by pricking their finger to get a drop of blood or using a continuous glucose ketone monitor on your cell phone. You will be able to know when you apply the GKI index, you will know exactly what zone of health you are in or not in. So you can know that you will be in a high risk red zone if you have a GKI that's over 50 up to 100. You are going to be in a zone of mitochondrial ill health.
Yeah. Can we backtrack quickly, Dr. Seyfried, sorry about that, and just briefly discuss what the glucose ketone index is, just for those in the audience who maybe aren't familiar with it. That it's just what the relation. Obviously, it's a biomarker that I know you have been intimately involved in developing. But yeah, what exactly is this index, and then how does it work? Obviously, we are monitoring two different biomarkers here: ketones, things like butyrhydroxybutyrate acetate, etc., and then obviously glucose. But how does looking at those two markers from a metabolic health standpoint help us to, well, determine metabolic health, and maybe just a bit more nuance there? I know there's generally a range there as well. I think you want to aim for about a 3 when looking to try and deal with things therapeutically. I may be wrong there. But yeah, if you could just fill us in sort of briefly just on what that index is all about.
So again, go back to evolutionary biology. Paleolithic man was always in a state of nutritional ketosis. Mainly because they did not have access to highly processed carbohydrates in their diet. So they had a lot of exercise, and they had a diet that was largely carnivorous with some vegetables, some tubers and this kind of thing. But they were complex carbs. They weren't these highly processed, like you mentioned already, high glycemic index kinds of things. So and food was limited. I mean, so when you put that body and you look at if they could look at their glucose and ketones at that stage, they would find themselves in a state of nutritional ketosis, which is an elevation of ketone bodies and a very low glucose level, or I should say, very normal like 65 to 85 milligram per deciliter, maybe 3.2 to 4 millimolar glucose. These are normal body levels of glucose produced by the combination of gluconeogenesis as well as carbohydrates that we would get from the diet. So we would always be in this beautiful super insulin sensitive zone, no insulin resistance at all, because diabetes would be unheard of. Type 2, of course, not type 1. Type 1 would have been afflicting us from the beginning of time in one way or another. But our bodies would have been in metabolic homeostasis as long as we weren't starving, of course. But we could go long periods of time without eating and still maintain metabolic homeostasis because we would be burning ketone bodies that would be mobilized from stored fat. So we developed the glucose ketone index as a marker, biomarker, to allow us to know what level of metabolic homeostasis we would be in. So, if you have a glucose ketone index of 20 or 10, I mean, you're in some level of metabolic homeostasis. If you want to go into a deeper level of what we call therapeutic ketosis, then you'd go down to two, a level of 2, which is the ratio of blood sugar divided by the ratio of beta hydroxybutyrate, which is the main ketone body. And then you would say, how do we know this? Because I have friends, Dom D'Agostino, Anthony Chaffee, and these guys, they're always in these states of nutritional ketosis. What do? They do a lot of exercise and they eat a lot of meat. And they stay in these Paleolithic kinds of zones. And these are the zones that keep your mitochondria super healthy. So what we do is we take people from the population and look at guys that have type 2 diabetes, obesity, and all these things, and you find these GKI values over 50, 100, sometimes above 100. Are you kidding me? I mean, it should be down in the 5 to 10 zone or 20 zone, and you got 200. Oh, I'm obese. I got systemic inflammation. Of course, you're not in metabolic homeostasis. So the glucose ketone index tells us. I built it for the cancer patients because we knew that if we lowered blood sugar down far enough, the tumor cells need the sugar to grow, and they can't switch to ketones. So you put them in a very compromised condition. Now, what we do, we see cancer shrinking down tremendously when you get the GKI 2.0 or below, but you still have the glutamine issue. So then we developed the press pulse therapy to come in and target with low dose of glutamine inhibitors while the person is in a state of nutritional ketosis.
And glutamine being the fermentable amino acid that is then
Yeah.
utilized as an alternative fuel source by various cancers in the absence of glucose. Is that correct?
Yeah. And people always ask me, what can you do what diet can I use to lower glutamine? And if I eat meat, won't that raise glutamine? The glutamine in our body is already super saturated because we use it for so many things, the gut and our immune system. We already have more than enough glutamine circulating in the body to provide a tumor cell with more than enough fuel in that regard. So there's no diet that will lower glutamine. The glutamine will always be there. So you can't, even if you do exercise, yes, you can lower glutamine, but it's not to the level where you're going to kill the tumor cell. So that's why we need drugs. But the drugs have to be strategic. While you're in nutritional ketosis, blood sugar is down, ketones are elevated. So you got a chokehold on the glucose pathway, but you got the glutamine pathway still opened. And then we come in with specific drugs that will block glutamine's availability. But we have to do this very strategically because the same fuel is needed by our immune cells. Our immune cells and our gut use the same fuel the tumor cells are using. So that's why we developed the press pulse. So we pulse glutamine. We do pulsing of glutamine targeting, killing tumor cells over a short period of time, removing the pulse, and allowing the immune system to come in and to pick up the dead corpses. So you have to have the undertakers coming in and get rid of the dead bodies in the microenvironment, and that's your immune system, and they need glutamine as well. So this is why you need to understand evolutionary biology and biochemistry to effectively manage cancer. If you don't understand biology and biochemistry and evolutionary biology, you are still in the Stone Age when it comes to this kind of stuff.
You're just peddling drugs and hoping for the best case scenario.
Yes, you don't know why things are working or how they work. We know exactly how things are working and why they work, and we try to perfect the system to keep these tumor cells under restricted fuel conditions, and the body itself, when increased in its health, will turn on the tumor cells and use them for fuel. It's called autolytic cannibalism. So the body itself, when put under energy restriction, every cell in the body must earn its existence in that body. There can be no weak, lame, inefficient cells because the body will turn on them and use them for fuel. The tumor itself becomes a fuel source for the rest of the body when you're put into these states of nutritional ketosis. So part of the solution to the problem is when the normal cells recognize a population of cells that are inefficient in utilization of energy, and they turn on them and dissolve them and use them for fuel. And that's people say, I don't know what happened to my tumor. It just kind of disappeared when I was in nutritional ketosis. Well, your damn body ate it. So because it was inefficient, they were using energy inefficiently, and the body recognizes that. And it's the term autolytic cannibalism. I published that. But we also can strategically target glutamine to work together. It's a whole systems approach to eliminating a bunch of cells that are growing out of control, using energy very inefficiently, being dependent predominantly on glucose and glutamine, and not being able to burn fatty acids or ketones. It's an elegant system. It's so beautiful. It works for the majority of people. And nobody's doing this. There's no clinical trial anywhere on the planet.
Can't make much money out of it, can you?
Well, the money issue now becomes another issue.
Yeah.
It's revenue first, patient outcome second. And I think people need to know that. They should know that their disease is supporting a giant industry. Many people are grateful for those who have cancer because the cancer patient supports a very lucrative process. That would be potentially disturbed if we were to find a method or a way to prevent or manage cancer effectively. But, man has made adjustments and adaptations to disruptive technologies, and they will do the same with this cancer and chronic disease situation. It's just a matter of time because we cannot continue on this path of this abysmal path that we've been on for the last 75, 100 years. So we will begin to change, but there will be new industries and new strategies for exploring and keeping people healthy and others. So we're trying to get a transition of revenue generation from one failed system to a system that really works, but has not yet been mature to replace the revenue lost from one system. But I think that's all part of the future as well. And but right now, my job is just to keep people alive with a higher quality of life using the knowledge of the biology and biochemistry of the disease that we understand.
Yeah, now that's fascinating, and I definitely would love to come back to that in a minute. I'd just like to quickly chat about the ketogenic diet a bit more, and I'm going to ask my question first, and then ramble on for a bit if you don't mind. I have a few concerns about sort of long-term utilization of the ketogenic diet, not for everybody, but just I have found that there are various people who do follow a ketogenic diet obviously are going to run into certain problems, some of them endocrine in nature, etc. Now, I think, of course, most people who are going to explore who are going to explore cancer treatment from a metabolic standpoint are going to utilize a ketogenic diet as their first step, and why should they not? Now, as I mentioned, I've got a few sort of concerns there. For example, I believe there's rodent data out there to show that a ketogenic diet long term may impair, I think it's hepatic FGF21 signaling due to receptor downregulation, and that there are other drivers issues there as well. for example, peripheral insulin resistance, which I'm sure you're familiar with. For the audience listening, that being the idea that in some people, long-term ketogenic diet adherence can essentially cause an insulin resistant like state at the level of the muscle, because the body is sort of not able or not readily utilizing the glucose at its disposal effectively. Now, I'm just sucking here, but I would be at least mechanistically concerned that those high levels of glucose might then also be a contributing factor if you're sort of becoming more and more insulin resistant. So the way I see it, just from the GKI score side of things, and again, this is just me piecing a few things together, but so tell me where I'm wrong, but are there other ways that you can sort of look at increasing your GKI score, maybe without necessarily utilizing long-term ketosis? And I suppose that's a question in itself. Should we always be in a state of ketosis, or should we sort of keep it for a period of time, such as when, hopefully not, you have a disease like this where it's needed? But beyond that, what about strategies where you are either intermittently fasting and obviously including a certain amount of carbohydrates in that eating window? Would that fasting period, obviously, again, the lower glycemic things, I'm not talking about swallowing large quantities of honey and processed sugar. And then, other fuel sources maybe that can sort of increase ketone production, your ketone esters, your NCT oils. Again, I hope that makes sense. I am rambling a bit, and as you no doubt already figured out, I'm definitely outside my wheelhouse here. But do you have any concerns, again, for the average person following a ketogenic for a longer period of time, perhaps in light of those mechanisms that I mentioned? And then beyond that, are those other strategies aimed at sort of improving a GKI index, maybe without being in a constant state of ketosis? Are they worth exploring, or is it just not enough to actually deal with the matter at hand?
Yeah, well, you got a lot of stuff that you just threw at me right there.
Sorry about that.
But we can break it down. But you're 100% correct. There's a lot of people who use ketogenic diets inappropriately that are not balanced with micro and macronutrients, which then can lead to some of the conditions that you mentioned in your
ramblings.
Yeah, in your ramblings. But I have seen the same thing. I mean, when we fed ketogenic diets to the mice or humans in an unrestricted way, diets that were not completely balanced in micro and macronutrients, we got many of the health issues that you mentioned were seen. The tumors actually grew faster. There was a complete metabolic inhomeostasis. You found conditions that would be reflective of some of what you have mentioned. That's why we try to get away from the term diet, and we talk about nutritional ketosis as a state of metabolic homeostasis, where your levels of ketones are not exorbitantly high and your levels of glucose are not exorbitantly low, but you are balanced in micro and macronutrients with a GKI of 5 or 10. And exactly as you said, in our new paper that we're working on right now, which will revolutionize the treatment of cancer and all these chronic diseases, we have built a color-coded chart to allow people to know what zones they're in at any given time and whether or not they can move effectively from one zone to the next. Like, yes, intermittent fasting, or the enjoyment, if you have been in a state of nutritional ketosis and you go out and party and your body then shows a much higher GKI, which would be unhealthy, you would then know what you would need to do to bring it back into a normal range with the types of foods and exercise. Exercise is extremely important. You can move these zones up and down, so you don't have to feel compelled to be locked into a particular state, but having the knowledge of what are the healthy states and what aren't the healthy states, knowing, like, for example, the Greek patients that did really well on the keto diet, it was a calorie restricted Mediterranean diet. Sardines, salmon, avocados, olive oil, and this kind of thing, that most people can do without too much difficulty. They had good GKI. They were very balanced in micro and macronutrients. But you could switch from that to a carnivore. There's a lot of flexibility in what a person can do to move in and out of these health zones without causing metabolic inhomeostasis. So we're working on that. We've published a big paper for the brain cancer patients to tell them exactly and address the questions that you raised. What are the choices? What are the variations that you can use to maintain constant pressure on tumor cells while constantly keeping the homeostasis of your normal cells at the highest level, and metabolic homeostasis? So we're working on that. And to address your questions, is most of the health problems associated with long-term ketogenic diets result from micro and macronutrient imbalances that lead to pathologies, some of which you have already elucidated. So once the base of knowledge becomes available for people, they can then build diets, and we call it nutritional ketosis, because you can achieve that with a carnivore diet, a Mediterranean diet, a pescatarian diet. Vegan diet's a little harder. Veganism, you have to supplement with micronutrients and some macronutrients in order to maintain metabolic homeostasis. It's not a natural situation. Humans did not evolve as vegans. If we were vegans, we would have been extinct a long time ago. So, but we are omnivores. Our bodies were evolved to eat anything walks, crawls, flies, or swims on this planet. And you can build nutritional ketosis from combinations of the natural foods that we evolved to eat. You just have to adjust the amounts that you're eating and the types that you're eating. So in our new study that will come out for managing cancer and chronic diseases, deals exactly with what you have mentioned, to allow people to always remain in a state of maximal metabolic homeostasis, but allowing the individual to know what zone of health they're in, to allow mitochondria to be as healthy as possible, and not too restrictive in rigidity in what you're doing, because part of enjoyment of life is the enjoyment of what we like to eat and drink, and we don't like to be pigeonholed into a particular way of doing something that eventually turns someone from being happy into miserable. But now with our new system that will come out on the apps, you will know at any given time what you can eat, for how long, and how healthy it can be. So everybody is a unique individual. We also have to recognize that we have sex differences, we have age differences, we have cultural differences, and we have religious differences. So people are in these cultural, religion, different ages and things. They have to build their diet and lifestyle around a GKI that meets their needs and keeps them in a comfortable zone. So and they'll know the quantification of that by looking at their glucose ketone index and matching it to a particular zone of health. So we will eliminate adverse effects, allowing people to be flexible so they can prevent these kinds of situations. And I think what we're running into now is people say, "Oh, I'm doing a keto. I'm eating lard every day." and I'm getting unhealthy. Yeah, who wouldn't get unhealthy? The question is, we want to eliminate those kinds of ambiguities in what people can and cannot eat, and give them the level of flexibility that will make it comfortable for their existence, while at the same time maintaining mitochondrial health. And I think knowledge is power, and every individual will adjust their own GKI and build their own diets and know how much exercise they need to do, and to keep their body in a state of nutritional and physical health. So this is the future. Um, but we're aware of everything you said. And when you start something off in the beginning, people sometimes overdo it. They do it the wrong way, and then they end up with these pathologies that become apparent, for, like you mentioned, with all these
Thyroid issues,
imbalances.
sex hormone
Yeah,
issues. Yeah.
yeah. I mean, that should not have to happen. Paleolithic man never had to deal with these things. His main problem was starvation. When you don't have any food, you starve to death.
Or at least your
So
ketones are high.
yeah, and well, you can only get ketones if you have normal hormonal insulin levels. Your ketones can never get ketoacidotic. That's type 1 diabetes predominantly, where you have very high glucose and very high ketones together in your body. That's pathological. Natural therapeutic ketosis is low glucose, elevated ketones, but not elevated to the level of ketoacid, because you piss out excess ketones. But when you don't have insulin, you keep all that in your body. Your body seems like it's starving. You can't get rid of you're making ketones in too high of a level, keeping too much in your body. So again, and we also know that there are some people that have carnitine deficiencies that can't metabolize ketones. There are people that get severe rashes from trying to get into these conditions. Um, and there's certain people take medications that interfere with the ability to metabolize ketone bodies. So we have to be aware of the interference of nutritional ketosis. But at least when you're aware, you can alert people to these hazards, metabolic hazards, and they can make adjustments themselves. So all of this, we have thought about all of this. Why? Because we don't do anything else in our life except think about these kinds of things. We're laser focused. We don't think about anything else except what you just talked about. Not just occasionally, 24/7. That's what we do.
Dr. Seyfried, thank you so much for that. That was incredible. Um, to be honest, I think I've got through 20% of the questions that I'd hoped to be able to talk to you about today. So I'm going to have to twist your arm somehow, God willing, into getting you back for round two at some point in the future. But
What was your main question that I did not answer?
Oh no, I wanted to go down the rabbit hole regarding various fatty acids, and specifically talk about saturated fats versus unsaturated fats, and the issues regarding some people running into insulin resistance, having sort of high amounts of saturated fats and the ceramides there. I don't know if you've seen that to be an issue
Well,
clinically at all.
we published a big paper looking at all that stuff in mice on restricted and unrestricted. It's hard to get into ketosis on polyunsaturated fatty acids, but the omega-3 fatty acids are very healthy for people. Some of the omega-6s are not. So we published a big paper on all this. So almost everything I have looked at in one way or the other. I just don't have time to talk about it all. But
Of course,
our
yeah.
open access papers on restricted and unrestricted diets, high carb, keto, and fish oil diets, and all this kind of stuff. So we have looked at that. And the body is a machine that metabolizes the fuels effectively. Ketones will be produced from saturated fat. MCT oil, little MCT oil, is really great in producing ketone bodies endogenously. D-beta hydroxybutyrate rather than L's. There's a way to do all that. We've looked at almost every damn thing we can look at. I have papers on that. But yes, we have looked at that. We try to do everything. Always again, remember, everything is metabolized, the majority in the mitochondria and the cytoplasm. So once you understand these metabolic pathways, you know how to keep your mitochondria as healthy as possible, which will make you, because ultimately you're interested in avoiding chronic disease. That's it. You don't want chronic disease. You don't want cancer. You don't want chronic disease. How do you prevent that? Keep your mitochondria healthy. How do you keep your mitochondria healthy? Keep glucose down and elevate ketones, the mitochondria. And I don't have time to talk, but in our new paper, we talk about the bioenergetics of burning fatty acids, ketone bodies, and pyruvate. The bioenergetic related to the delta G prime ATP hydrolysis, and how we can get more bang for your buck. Every breath of air can give you more ATP when you're burning ketone body than when you're burning pyruvate or fatty acids. So we know the bioenergetics. We published that, and our big paper is going to be coming out on that. And we got all that from the late Richard Veitch, one of the great, and he was Hans Krebs's last graduate student. So he and I would talk for hours and hours and hours about all the bioenergetics of mitochondria and what you need to keep it healthy and functional. So there's a strong bioenergetic explanation for a lot of what I'm saying, and that's in our papers.
Yeah, we'll definitely be sure to link them in all the show notes there.
Yeah, make sure. Yeah, tell folks that all of our papers are open access, so anybody with a computer can get the information. Now, people are going to be overwhelmed and say, "Oh my God, Seyfried published so many papers." Yeah, well, a lot of it's on what I'm talking about. A lot of it's on other things, but you can go through and ferret out what we're doing, and people need to know that all of our research is supported by philanthropy and private foundations. So we get when we keep people alive who are stage 4 cancer, they so-called terminal, and all of a sudden you're living a lot longer with a higher quality of life. Some people feel very compelled to donate to our research because they want to and one thing I want to make sure, never say we have a cure for cancer, because I have no clue whether what we do will cure cancer or not. The only thing that we have seen over and over again is we have a longer progression-free survival without symptoms, and a very increased overall survival of cancer patients. Whether they're cured or not, we don't know. But I consider success in keeping people given terminal diagnosis alive far, far longer than what the establishment predicted their lifespan to be. So I never like to use the term terminal, because I have a lot of people that I know who are still alive. I don't know. Sometime in the future they may be terminal, but they're not dead yet, and they're pretty healthy. So what the hell does that mean? And they were told they only had 9 months to live, and they're out 6 years. Who made the mistake there? Why was someone told they have 6 months or a year to live, and they're living 5 and 6 years or even longer? How did anybody make that level of mistake? They made the mistake because they don't understand metabolic therapy and how long you can possibly live with a higher quality of life. But whether you get a cure or not, I have no clue. All we know is we have a new strategy for managing cancer and chronic disease that is far more powerful and successful than anything out there right now. The problem is people just don't know about it and don't know how to implement it yet. And that will be the future.
That will be down to people like us aiming to educate the greater public. Dr. Seyfried, thank you so much for your time. For people who are interested in your work and to learn more about your various metabolic therapies, where can we point them to?
Well, again, I have my metabolic papers already published, open access, and donations go to Travis Christofferson's Foundation for Cancer Metabolic Therapy. It's a legitimate foundation, and the university, Boston College itself, the biology department for sure. So that keeps us going, and we've got a couple of blockbuster things coming out that are really going to transform the healthcare industry dramatically, and they'll be out within the year, and then you're going to see organizations set up around these approaches for metabolic health, and we're going to bring a lot of people back into what we call normalcy, metabolic homeostasis, if they want to.
Yes.
I'm not twisting anybody's arm here. It's only if people who want to. If they want to live in a toxic state, that's their choice. But we have a tool now to allow them to come out of those toxic states and live a healthy, productive life with a clear quantitative assessment to do that. And that is coming down, and you'll see that within the next year or two, for sure. So we're very hopeful for managing chronic diseases, and I think most people are going to be very appreciative as they begin to benefit from what we're doing.
No, I'm sure they will. And it's just about, I mean, ultimately, I think most disease, the way I'm starting to view it, is it ultimately comes down to sort of removing the environmental burden or whatever environmental trigger there is that's driving the disease, improving the metabolic health and subsequently the mitochondrial health, and then dealing with the stress component, which is also obviously overlooked. And I think when you get those three sort of components sort of dialed in, you sort of solve 90% of the equation, at least when it comes to chronic disease.
Which is mostly crippling Western societies.
Yes.
So it's the single most biggest problem. Cancer and chronic diseases are dementia, type 2 diabetes, obesity, cardiovascular disease, cancer. You can go right down the list. It's just like everything. So what do we do with all these healthy people if they, well, I think we're keeping a lot of people alive, working for a longer period of time with a higher quality of life. I mean, you're going to have a readjustment of society. So
yeah. Well, let's aim to get there, and then we can deal with that problem when it arises.
Yes, absolutely. All right. Well, listen, thank you very much.
Thank you, Dr. Seyfried. It's been an absolute honor, and I appreciate your time.
Yeah. Well, thank you. I'll let you go now.